If you can show that groups have the same generators and relations, is that sufficient to show that they're isomorphic?
Yes, if it incorporates the whole group. We're going to get into more subtle that, but for right now, you can take that as. So if you have, so I think I know where you're going. You're looking at sort of, you're thinking about the dihedral problem. What you know is the group was generated by two elements of order two, right? That's all, and it was a finite group. What you can do is you can show that the dihedral group, which was generated by, or you can show that the group generated by X and XY is also so the strategy in that problem was that the group generated by two elements of order two, and this is the key. Show these are equal, right? You okay with that? So you show, certainly you always have this containment. And this containment, because any XY is contained in here and X is contained in here. And the reason you get the other containment is because what do you need to do? You need to make sure you can generate an X here, but you can because you can write X, Y times X. Because the group generated by two things includes both the inverses as well. So you get an equality here. Since you have an equality, what this has, this generates a little subgroup of dihedral on the end dot, right? Where it will best place, say n. Right. So now what you have is this group, your parent group to start out with, has a subgroup that is dihedral. And there's your rotation and there's your flip. Right? But you have equality here, so the whole group is dihedral. Right? Is that the question that you were trying to deal with there?
Not precisely. I mean, that is the problem, but that's just why is it insufficient to just show that you have, because you both groups have two generators that are of the same order, so they're essentially the same. Why is it not sufficient simply to show that the generators in our group satisfy the properties, the relations of the generators in the other group?
So here's the problem. That's dihedral. Yeah, right. Here's another group that satisfies this relation, the identity group. Right? Because identity squared, x squared is the identity, and identity is identity. So that's why, so what happens is the largest group that satisfies these relations, every other group that satisfies these relations is a homomorphic image of them. Right? So when I have these relations here, there is sort of this largest group that is generated by this, in this case, dihedral. Any other group that satisfies these relations may be smaller, right? The identity group has sort of extra relations that I haven't listed here. The identity group also has the relations y equals e and x equals e. Right? But certainly the identity group satisfies these relations, right? And so we're actually going to talk about that when we get to free groups a little bit. But the equality here was actually something here because what we have is we have this xy is of order n, x is of order 2, so you know it's not the identity. And you can take it as given that I gave you earlier. When you have a group that satisfies those particular relations, it's dihedral. Okay. Any other questions? So, what we were talking about last time is we had talked about normality, and we were getting into this business where we counted elements of HK, where H was a subgroup. We're going to do a little bit more of this kind of thing, and then we're going to talk about quotients and the isomorphism there. So, the last thing I left you with was this theorem. So what we had is K and N are separate to G. And N is normal. Number A. N intersect K is normal K. N is normal. And the join of N and K. Let me recall for you that this is the smallest group that contains all of N and all of K. Number C, number D, if K is also normal in G, and K intersect N is the identity, then K and K are all N and N. K. Okay. Let's go through proof of this. It's pretty easy actually. So let's suppose we have an element of N intersect K, and suppose K is K. Then K inverse XK is in K. So no problem there, because both K and X are K. And K inverse XK is in N as N normal G. When you conjugate X by anything in G, it's still an N, in particular if you conjugate it by K, because K is known as well. Number B, N is normal in showing here. Well, I claim it suffices to show that for all K and K, K inverse K is an N. And this is true since N is going and K is separate. Well, why does it suffice? Why does it suffice to show that if you conjugate anything in N by K, then you're good to go? Well, in general, what does an element of this look like? Remember, this is the smallest group that contains both K and N. So you can think of the elements of K and N as just sort of letters in your alphabet. And a typical element of this will be any word that can be made by elements of K and N, or their inverses. And I'm not going to make that distinction here because since K and N are both groups, subgroups of G, then if it contains a K, it contains a K inverse. So I won't make any distinction. A typical element K1, N1 up to K, with K, N, N. I'll call this X. Now you might criticize me and say, well, Jim, how do you know you started with a K and ended with an N? And my answer to you would be, well, I could just take K1 to be the identity, and I could start with an N, or I could take this one to be the identity. So I think this is general enough. Are you okay with that? And what we need to do is show that when you conjugate anything by something in K, so let Y be in K. Well, if you look at Y inverse at Y, this is Y inverse K1, N1, K2, N2. I'm writing it out for matter purposes. Kn, N, M, Y. Well, what I can do in a very Thompson spirited way is now, these are all in K because the K's and the Y are all in K. And these are all in N because N is normal. And so therefore this product is still in small group generator. Questions? Let's look at C real quick. So we want to show that NK is equal to, so first let's show there. Let me point out that this is true because this set actually contains all of N and all of K. And so actually, right. So anything in NK is certainly in here because this is the group. So I've got all of N in here, I've got all of K in there, you get a product. So it suffices to show group. To this end, I think it's pretty clear this is a non-empty set because this at least contains the identity, right? So take a pair of elements in here, M1, K1, and N2, K2, and I want to show that that the product is in there. Let's see which one's normal. Yeah. So in two inverse, right? Now, my goal is to show that this is in K, right? And what do I know? I know that N is normal, right? So what can I do? Oh dear, what can I do? So how do I, so my goal is I'm trying, you guys perhaps see what I'm gonna do. I'm trying to do the subtrate criterion. So here I have something in NK, something else in NK. I need to show this times the inverse is still in NK. So I need to be able to write this as something in N, something in K. Right? So really, I guess I need to write this as K, but the problem is I've got this, this thing right off the table. Any ideas what I can do? I think I know what to do. So we do this here. Okay, well, I just stuck that on there. That's no good. Once I balance it out. Everybody okay with that? What am I doing? Am I having a stroke up here? What's going on? Yes.
Now, two elements on either side are in N, so N1 times that element, and then everything on the right is in K, so it creates one element.
Good. This is K2, K1 inverse into inverse, K2, K1 inverse, that's K1. This thing is in K. This thing is in N because N is normal, right? Because basically I've taken this element of N and I've concatenated it, and this is in N as well, so this is in N. That means that this is a subgroup and it contains all of N and all of K. This gives you the reverse containment, you have the equality. The proof for Kn is symmetric. In fact, this is kind of a fun thing you might want to prove for yourself. Nk is equal to Kn if and only if Kn is group. Okay. Questions? Okay, let's do this last one. Be a little bit careful about this. This does not claim that Nk is a billion. This just means that when you have an element of K and you have an element of N, you can turn around willy-nilly. The elements of K, when they meet each other, may not commute. The elements of N may not, but in K, it's the same thing as Kn. Let's prove this. So you also have K is normal, E, and K intersect N, the identity. Consider, we talked about this last time, the commutator, N inverse K inverse Nk. Notice that this is N, well, that's an N, right? So you have N inverse times something in N, this is an N. And you also have, because of the fact that now K is normal, that this thing is in K, and that's in K, so this is in N and intersect K, which is the identity. Therefore, N inverse K inverse Nk is E, and I get Nk is K. Okay. Any questions on that? Okay, so here's where we introduce so-called closure group. Go on, online statement. Take over control. Oh, you guys can't see the board, you need to holler at me. Chat at me. Yeah, you all at home, don't be shy about hollering out. It's like this is, Okay. Questions? All right, so let me give you the following theorem. And this is where we introduce the so-called quotient group. Suppose that G is a group and N is a normal subgroup. And normal in G, then on N, set left cosets of N and D. This could be right cosets too. I just prefer to do it this way. Is a group under. Okay, so what is a group? A group is first and foremost a non-empty set. Well, no problemo. I've got that because G is not empty, so its left cosets are non-empty. And I have to tell you how I can multiply. Now, I don't know much, but if I'm gonna have a group, it's gotta be closed into the operation. So input, 2 cosets, this has to barf out a new coset. Blank G. And let me tell you, I preach the gospel all the time. The gospel here is, if it's in math, if it ain't easy, don't do it. What is the most obvious thing to do? Something that even I, parents who are cousins, can remember is that. This is how we do it. Now, let me point out a couple of things. The fact that this is a group is sort of easy, modulo one fact. And the one fact, it's not any of the regular properties of group you expect, not the associativity, not any of that stuff. It's really the fact that this thing is a well-defined operation, right? So, proof here. This is a biggie, right? Because remember, what we're talking about cosets. And cosets usually have many representatives. So if I pick G1 and G2, those are my representatives that I elect for those cosets. If you go elect A and B for the cosets, well, so if A and B and X n equals Y n, then A n X n equals B n. Right? Because here I am electing my representatives A and X. My output is going to be AX n. You elect, through no fault of your own, you just pick some other representative, B and N, you get BY out of this, right? So we need to show that AX n BY. Because when I pick my representatives, I'm gonna get this answer. When you pick your representative, you're gonna get this answer. We have to agree. Otherwise, my rule of multiplication makes no sense at all. In fact, you exactly need normality here. So let's kind of collect what this means. And I don't know how this can play out, but VA inverse is in, and actually I'll make it inverse too. A inverse C, say, in. Right, this is what we meant by congruence modulo n. Notice that these two are inverses of each other, and I'll write them both down because I don't know which one we'll use. We also have xn, yn, if and only y inverse x, that is the same thing for the full x inverse y, or n. Right. So let's see what we can do with this. Probably take one. So what this means is, I guess what we need to show is V inverse, Y inverse. So in the spirit, we need to show V inverse, say, Y inverse, AX, and now, of course, it's very instinctive to kind of sort of start putting this together, right? But is everybody cool with that? This will solve our problem, right? Because if this is true, this is equivalent to AXN. AXN.
Does it matter if it's like?
Oh, actually, I'm glad we said that. I think I did that right. Or I did that wrong. It's actually the other way. I'm glad I wrote that down because this should be Y inverse. Yeah, be Y inverse, B inverse, A, X. Is that what you were going to say?
Yeah.
Yes, ma'am. Yeah, that's a good catch because the order is going to matter here. Okay, so y'all see how we can do this given our tools here? See, it looks to me like this part is in, but then it's spread out by this. And so how am I going to get that? There's one thing I haven't used yet. And what do you think is going to be crucial here? The normality then, right? So, what do we have here? Well, so let me try something here. So we know B inverse A is an N. That's of course by the fact that cosets A and B represent the same thing. Now, it's very natural for me to do this. Kind of see where I'm going here. Everybody okay with that? That's just here. Where I've used normality. Anybody got any ideas?
One through six. There you go.
Y inverse X is in N. So Y inverse X becomes X inverse B inverse A X is also in N. and this simplifies to y inverse b inverse a x. So, well defined. And it's an if only, this step right here, very crucial, the normality. This does not work, it's not well defined, come on. But once it's well defined, you totally got it licked, because the identity, if you look at our rule of multiplication, is exactly that. Given that, what's the inverse of the coset Gn? G inverse n. Because when I multiply G inverse n by Gn by our rule, that's G inverse, which is the identity comes in. It's clearly closed, right? Just by the way we set things up. And associativity actually follows from G. The fact that G isn't was associated in the first place gets the multiplication associated. So once you know the well-definedness, you've totally got this baby. Let me give you a proposition to sort of follow up on that. And in fact, some people talk about quotient groups, not just to the quotient group itself. We're going to call G mod a quotient group, but it's also a somehow proposition. But in a normal and mean, then the function n and G mod n given by n Gn with an anthropomorphism. This is clearly onto, right? Because no matter what coset you want, it comes from whatever representative you have to pick, right? Also, phi n of G1, G2 is G1, G2 n, which is G1 n, G2 n. Because that's the way we multiply these things, which is pi and Q1, pi. So on to homomorphism. And in fact, for an example, it's probably a bit familiar, we'll look more sophisticated ones. I'll give you another example here. Actually, here, yeah. Actually, yeah, 0 will take the work too. But, by the way, some of you might have fun in my math book talk this Friday, because I'm going to talk about modular arithmetic, which I know you all have probably all seen a lot of, but there's still some fun things that maybe I can show you. Anyway, so the way this homomorphism works is your input is an integer k, and you just reduce k mod n. Divide it by n, see what the remainder is, call that k bar. This is a homomorphism from z to zn with the kernel in z, which is, so here, this is, we identify with this is z mod n z. Here's another one. Z from Sn z 0, 1 addition. Anybody know what a homomorphism here is? This again is going to appeal to your former knowledge of maybe symmetric groups and alternating groups a little bit. We'll talk about this more later. P of sigma is equal to, anybody think of a natural way to take an element of SN and associate to it an element of Z2? This is 0, if sigma is even. And 1 if sigma is odd. This gives you a homomorphism from Sn in Z2, and the kernel of B is actually equal to AN. So you can identify this with isomorphic to Sn mod AN. And here, I guess what I want is N to be greater than or equal to 3. Well, yeah, N is greater than or equal to 2. Now, the one thing that you know that I haven't proved yet in this example is the fact that this function is well defined, right? Because, for example, if you have a permutation that can be both even and odd, this doesn't work, right? It's not well defined. Now, probably most of you know from your past experience that permutations are either even or odd, not both. I am going to formally prove that later. So let me give you, so this, I might consider this kind of a fancy pants version of the first isomorphism theorem. I'm going to get this corollary first isomorphism theorem. So let me write this down. And this will, I'm going to look at a lot of theorems in this class this way. Isomorphism theorems, theorems about direct products, direct sums, and so forth. So let F from G to H be a homomorphism of groups. And let N be a normal subgroup contained in the kernel of F. Remember, one of the things that we talked about already is the kernel of F is always a normal subgroup. So I'm going to generalize this a little bit. Let's say that N is some arbitrary normal subgroup with the stipulation that is contained in the kernel. Might be the kernel itself, might be the identity, or might be something intermediate that happens to be normal. Then there exists a homomorphism. It's sort of induced by F. So I'll call this F bar. Line N and F. Such that, well, I'm going to tell you how it works. Such that F bar of AN, let's see, this has your inputs are cosets, your output has to be something of H is F of A. So you read the coset, you go to F of A. I guess I'm gonna have to worry about that being well defined. What is more, the image of F the image of F and the image of F bar coincide, and the kernel of F So actually, I'm gonna draw you a picture of this. Draw a picture in algebra, but I'm gonna do a number of kind of things here. Okay, so let's kind of sort through this. You start off, somebody walks up to you and gives you a homomorphism from G to H, and N is a normal subgroup kernel. Well, whatever this normal subgroup is, you can sort of use this homomorphism to induce a homomorphism from G mod N also into H. Just by reading the coset and doing what F would do to the coset representative. The image is the same, so you cover everything in H that the original F did, and the kernel of this homomorphism is whatever the kernel of the original one was, modulo this new guy N. So you have this E into H. So we had this original homomorphism. We have, by the way, what do you suppose is the homomorphism I would use from G to G mod N? How about that animal? And so what we have is we have this induced homomorphism. Such that this symbol means the diagram commutes. So that is, if I start at G and go to F, doing F, that's the same thing as going here and here. So doing pi N and then doing F bar is the same thing as doing F. So, by the way, it's probably worth noting at this point that you might ask yourself, when is that bar an isomorphism? Well, you need two things. You need for the original F to be onto, if you believe this, because their images are the same thing. And so for F bar to cover H, you need F to cover H. And what else do you need for this to be an isomorphism? You need for N to be the kernel of, you need this inequality, so you get the trivial. Okay, any questions on that so far? This is one of the things, this is one of those things where I think proof of excellence will help us in our understanding a little bit. So I told you what the function is, F bar and N. Okay. The first thing we need to do is we need to show that this is well defined, right? This is the usual problem. Well, suppose AN equals DN. This implies that D inverse A is a because that's what it means for these to be equivalent. So F B inverse A must be the identity, right? As N is subgroup of kernel by assumption. Therefore, F B inverse F A is the identity of H. So F A, and by definition, therefore, F bar of AN. So, well defined. Right. You pick A for your representative, I pick B, and we get the same answer. Okay. What other statements do I need? The fact this is a homomorphism is just like before. Now this is fairly straightforward. So if you look at F R of A N X N, this is F bar of A X N. Because after all, that's the way we multiply cosets. And this is F of AX, which is F of A F of X. So F, originally, the original F was a homomorphism. So this is F bar A N, F bar. So this is a homomorphism. Obviously going into H, because that's where F went. Let's see what we can do about the rest. Note image F is equal to image R. Because any F of A in the image is mapped to by this, right? And of course, anything here by definition is in the image, so we've got both sets of containments. And let Xn be an internal of F bar, then F bar of Xn equals F of X, the identity of H. Therefore, X of F. So I'll let you finish up the details on this. Check also that this composition is exactly as I claimed, right? When you start with something here, say A and G, this goes to the coset AN, which by definition goes to FA. And so the diagram doesn't matter which way you go, you end up at the same traffic stop. So let me throw this out here. I think there's some time for this. Let me give you a corollary to this really nifty result. This one's a little bit more general than what you're used to. This is the famous first, and in my humble opinion, best isomorphism. Well, actually, all the other isomorphism theorems, this is a big tool in showing that. So there you go. If A is a homomorphism, then F induces an isomorphism. G on the kernel of F, given by F bar, say G kernel of F. Let me remind you that that's a subgroup, so this is a coset. Subgroup is a normal subgroup kernel of F. This is an immediate application of this. I think that's good timing. Any questions? Any questions on this? Okay, well, if you all have any questions coming up, how about y'all out there? Anybody got any questions? Okay, well, if there's any homework, I'll be in my office. Let me know if I can help you out. Other than that, y'all roll on and have a good day.